Thank you, Inmar. Thanks, Tommy, for putting this robotics day together. It's really exciting to be able to speak about Kindred. It's the first time speaking about Kindred. Like I said, co-founder and CTO at Kindred. Kindred is a startup that doesn't have a lot of public-facing material right now, so you're going to get a sneak peek into what we've been working on for the last 2 to 3 years. It's a very high-level talk. It's a short talk, but I hope you'll find something interesting and maybe entertaining. Kindred was founded 3 years ago to build machines with human-like intelligence. It's an ambitious objective, to be sure, but there are so many exciting developments in machine learning and so much potential for good, I think, that can come of capabilities that it would take to build machines with human-like intelligence. That's what we're going for. Like Inmar said, we have 3 teams. There's a team in Toronto, a team in San Francisco, and a team in Vancouver. It's a Canadian team. It's a Canadian company still. We have a number of, I'm not sure if the pictures are big enough, but there's a number of supportive affiliations, investors and advisors from some of the, I would say, some of the greatest companies and universities in the world doing research on this kind of thing right now, and it's great to have their support. I'm going to start the talk by quoting Andrew Ng. Andrew has spoken recently about AI as being the new electricity. Electricity obviously revolutionized the way people solve problems, and AI is doing that now. The cycle that's been drawn up here is a cycle in which if a product can attract users, as Ryan was talking about, the natural interaction between the users and the product creates data as a byproduct, and that data can be fed back into AI to improve the product, to create a virtuous cycle. And that virtuous cycle has created speech recognition that actually works. It has revolutionized computer vision, the way people think about doing language processing. And it's in the process of creating AI drivers for autonomous cars. Amazing things. And even a lot of that core work driving all that stuff happened here at University of Toronto for 2 decades. And this cycle is our inspiration for thinking we actually have a shot and a strategy at building human-like intelligence in machines.
I got a message from somebody watching this on live stream saying that it's hard to hear you because it's switching between the audio and the room audio.
I'll just switch to this one then.
Maybe just talk about it.
All right. So I'm going to talk about Kindred's efforts are operating largely under the assumption that the leap from today's AI to human-like intelligence requires a body to be fully realized. And not just any body, but a body with similar kinds of sensors and actuators to a person. It's not clear yet, obviously, exactly how similar that has to be. How far do we have to go? But we're pretty confident that a cell phone isn't close enough. It doesn't have arms, doesn't have legs, doesn't have hands. We believe that a body is required to learn language, incidentally. And language is the central part of the way people form relationships with each other. It's a core thing about being human. We conjecture that's maybe even why we have language. I'm going to give a quick example about what you could do with a disembodied intelligence. It doesn't have any body. Imagine you could buy something like this off the shelf, and it was the latest product from Amazon or Google or something. And it's some kind of a device that can sort of see some cameras and do some image analysis. And imagine it worked amazingly well. So supposing you're trying to take care of an ailing grandmother and you want some kind of AI to help. You install this thing in a house, and I think this is about the best you could do. You set it up, and lo and behold, some computer vision algorithm successfully determines that, without any false positives or false negatives, something terrible has actually happened to your grandmother. She's fallen on the stairs. She's in pain. She needs help. Now what? You know, it can maybe be smart about contacting somebody from your address book, but your grandmother is a physical thing. You're a physical thing. Her body's in trouble, and what she's really going to need here is some genuine physical assistance. So what we're imagining is the kind of AI that it would take to have more like this kind of conversation, if you're still going to be talking to the AI with your cell phone. This is a bit sci-fi, but this is the kind of intelligence that we're going for. Like, that's what success, I think, would look like. We want to have an AI that's got the situation under control, that can make her tea, get her onto the couch and get her comfortable, download the latest medical knowledge to be able to do an analysis and decide if she's actually in need of further attention and fix the stairs. So we're not there yet, but I'm going to tell you a bit about how far we are. AI is the new electricity, then Kindred is a power plant, an AI plant, and the creator of the devices that use it. So we're imagining we have already built and we're envisioning a system that has these different kinds of components. There's a general embodiable kind of intelligence that would be available maybe centrally over the internet. And so we're coming up with kind of like APIs for what that sort of intelligence might be. At the same time, we're building the first generations of robot bodies and control algorithms that would use that kind of AI plug into it. So to be clear, at the moment, to get the virtuous cycle that Andrew Ng talked about, to get it started, we're using human operators in real time as a general intelligence. We call these people pilots. They get to pilot these bodies. We've developed a number of piloting interfaces that involve virtual reality, as well as keyboard, mouse, and touchscreen, that sort of thing. So people can inhabit a remote body and feel that they are a robot. It's really cool. It's a really cool thing to do, to experience. And what this lets us do is instantly take control of robots with skill and generality that are light years beyond the state of the art. And it really highlights how much of a gap there is between robots that can be built and the control systems that we have right now that could run around. As an example of the kind of robot that we have, this is a robot with a human computer hybrid intelligence. We call it Cube. It's a 6 degree of freedom arm with a pinch gripper. I'll just start the video over here. So I'll just talk over it. It's a 6 degree of freedom arm with a pinch gripper mounted inside of a plexiglass case. In this video, there's sensory feedback from the arm and the gripper, and there's also like a video camera that's mounted on the just on the inside of that top edge there, so you can see. If you're inhabiting this robot, you can see the working area through that camera. And in this video, Cube is doing a pick and place with a set of objects that we did not program it for. And as you can see, it is generalizing exceedingly well. It does just fine. It can handle anything the gripper is physically capable of, which is stuff that's not maybe too big for just one little pinch gripper. And it can crank through about 600 things an hour with this setup. It's well beyond the state of the art for the sort of general pick and place product that might be an alternative. And the key to this generalization is to use human intelligence that's been engaged via virtual reality. This used a HTC Vive based VR setup. And the reason it works is because the human pilot in this video has about 25 years of general life experience going into this, and about 2 days of experience on the specific robot. And if I would bet that this particular pilot here, and we could call him Max, hypothetically, can probably pick up anything from a Tide bottle to a plastic straw, anywhere in the working space, in any orientation, in the middle of clutter, buried underneath stuff, bent in half, and so on, in probably about less than 5 seconds. And even if the fingers on the gripper got stuck, a human pilot could figure out a workaround. No algorithm can do that. Another important thing to note about Cube's performance here is that it's not piloted the whole time. So if I just replay it again, I'll draw your attention to a seamless, maybe a transition some of you might have noticed. That part of the off-duty cycle is handled by an algorithm, that path planning, and it whizzes around from front to back and you put something in one of those output areas. And then it whips back over here, and then right about there, I'm not sure if you even saw it, there was a transition from an algorithmic control into control by the pilot that's engaged by virtual reality. And so that the human intelligence is only used for about 3 or 4 or 5 seconds out of that duty cycle. So here the human intelligence is used what human intelligence is good for. The computer is handling what algorithms are good for, and they make a good team. And they collect that sort of data that drives the virtuous cycle. So the kind of intelligence algorithm, there's sort of a general schema that comes up in building control systems for the robots the way we're thinking about it. There's sensory inputs that I've drawn in orange at the top, which feed into kind of 2 streams of controller. One's based on a remote control, one's based on local control. And the remote control is in constant contact with like a matchmaking module, which brokers connections between a pool of available pilots and sorry, I got distracted by the sign. A pool of available pilots and the local robot that's actually trying to do some stuff. And then there's an actuation policy that is brokering the switch back and forth, deciding when to use a remote general intelligence and when to use a local one. Another robot we've built according to this schema is our first product. Here, I can just start the video. First product is a machine kind of related to the first one. It's got a bit more pieces. It's designed to be suitable for deployment in a customer's facility. There's a barcode scanner inside that can recognize objects and put them in appropriate, so the arm can put them in the right spot. The mind of this robot has been designed to sometimes grasp things automatically as well as use a person, so that that module that switches back and forth has a bit more like there's uncertainty and confidence estimates that happen inside as it brokers between a number of competing algorithms to do the grasping. What you're looking at here is piloted grasps, but there's a number of algorithms that we have in development that are coming along very well. So we have Cube, that was a plexiglass robot. We've got this bigger robot that we call, sometimes we call an orb. I'm not sure if that's going to be the final name for it. There's other robots that we prototyped. There's different pilots that we have on call. And so what we're imagining building is this network of learning minds and bodies. This is a real-time control network. So you can imagine data flowing every which way. And all these bodies try to do smart stuff in their various contexts. The first kind of learning, and this is where the data comes in. There's a couple of roles for data to talk about here. All of the general intelligences in our system are currently humans, but our goal is to add human mimic AGIs to that pool as well. If we can model human behavior or use inverse reinforcement learning techniques or other data-driven modeling kinds of things, you can imagine adding algorithms to a pool of general intelligences, and this is what I think is the closest thing anybody has proposed to a specific definition of artificial general intelligence. Our definition is that if an algorithm can plug in and handle the diversity of tasks that a person handles, then that's our target there. There's another kind of learning which is more like apprenticeship learning. As data flows into the robot bodies to make them do specific things, we can see how that's helping the robots to learn from that experience. So that in the context of specific robots, they can get better over time. And then there's a number of challenges, a diverse set of machine learning things that happen just within individual robot control systems to do autonomous grasping. And you can use the general intelligence as kind of like offline to collect annotations and so on. So there's a number of different so-called virtuous cycles happening. Thanks for your time. Thanks to Omi Myanmar for organizing this. Thanks everyone for coming. Kindred is hiring. If you'd like to know more about the current open positions or an internship, please feel free to contact Myanmar. She'll be here later today. There's some addresses up on the slides that you can see what kind of positions we have. There's some sort of fun videos up on the top right there. Thank you for your time. Thanks for coming.